Hello, we are Group 19. We are presenting on our Tommy John surgery predictor. Starting with the abstract, the objective of this study was to identify factors correlated with the rise of ulnar collateral ligament injuries. The data was sourced from Baseball Savant. The data was used to train several models such as LSTM, XGBoost, and logistic regression. Ultimately, this study found that the logistic regression model produced the best results. There is a stable enough relationship between UCL injuries and the influencing factors such that the linear models produce the most accurate results. Our findings indicate that publicly available season-to-season pitching metrics are not robust enough in order to accurately predict UCL ruptures. This may indicate that we need to look more intensively at month-to-month or even game-to-game metrics. Alternatively, it could indicate that risks begin before they are able to be accurately measured. Even though our best performing model was not consistently able to predict the possibility of injury and only achieved a moderate discriminative ability of 0.64, its coefficients revealed a consistent patterns in the data, suggesting that total innings pitch tempo, and increase in games played were the most strongly correlated with an elevated injury risk, which is consistent with previous literature.
What is Tommy John surgery? Tommy John surgery is a surgery that is aimed to fix the UCL, or the ulnar collateral ligament. And that ligament is located in the inner elbow, and it's supposed to stabilize the inner elbow. Pitchers tend to utilize the UCL a lot, especially when they have to pitch as accurate as they do. Starting pitchers will tend to pitch around 60 to 80 pitches per game, with relief pitchers and closers pitching around 20 to 40, which means pitchers tend to use their UCL a lot for stability. The recovery for this surgery can be quite costly and time consuming, with the full recovery time being around 10 to 18 months. And that can include just letting the muscle heal from surgery, not putting it under any stress, and then after that, all the physical therapy that is needed to get them back to full strength. The scientific community currently identifies the number of innings pitched per season, the number of pitches per game, months pitched per year, poor throwing mechanics, and pitch velocity as the main risk factors for the UCL surgery. And another factor that people are starting to add to the discussion is spin rate, or the increase of it. What spin rate is the amount of spin that the ball has when it's in the air. And pitchers utilize spin rate a lot to create more movement so that pitches are harder to hit, which can cause the UCL to be utilized more and be put under stress more. Our motivation for the project essentially comes down to that there is a growing risk or a growing concern due to rising rates of Tommy John surgery. From 1996 to 2016, the rate of UCL reconstruction surgeries per year tripled. And on this graph right here, from 1999 to 2012, we can see that the rate of Tommy John surgery per year has increased by 4 times, almost 5 times.
Sourced our data from a number of different places, including Baseball Savant, Baseball Reference, and Fangraphs. For the statistics and the player IDs were sourced from Baseball Bureau Persons Register, Timothy Fisher's Player ID database. And finally, we use MLB player analysis's surgery list in order to determine who had the surgery. So we had to aggregate all of this data together, and starting off, we just dropped irrelevant or unfillable null data. We had to convert player IDs into one consistent register because each one used a different identification system. Then we slowly combined all the CSVs into one usable data frame and aligned features, converted units that weren't the same. We aggregated the stats, cases where a player was sent up to the majors or sent down to the minors multiple times in one season, so they had multiple entries for that same season. Furthermore, we also backfilled player averages wherever it was possible in order to get rid of any other null data. And lastly, we engineered delta features in order to measure workload across seasons.
For the model architecture, we tried a couple different models. We started out with a simple RNN, but we realized that that didn't really suit our goals because it was too simple. So then we moved on to an LSTM. We also used logistic regression kind of as a baseline for our model. We also used XGBoost and random forest. Our reasoning behind why we thought LSTM would be a good choice for our data is because our data is sequential in nature, which makes it a good fit for LSTM. So this is what we used for our model architecture. Obviously, this is just one example of what we used and what worked best. We tried several different values for each hyperparameter. A major problem we ran into is that there are significantly more people who haven't gotten Tommy John surgery than people who have, which caused our models to just predict everything at zero. So to try and mitigate that, we used focal loss, where you penalize misclassified positives more heavily. We also had to change the class weights, where we were weighing the positives more. We also tried upsampling. Also, later on, we tried brute forcing, which had worked a little bit better. So here are the evaluation metrics that we used. The main metric we were using to decide whether or not this would be a successful model is recall precision and the F1 score. We also monitored the precision recall curve in addition to those. So for us, a score of zero point 0.7 for our F1 score is considered a good score. And for recall, it would be 0.8 or above. In cases where we needed to prioritize recall over precision, false negatives would be heavily penalized. And some other metrics for succeeding is that we are able to identify features that correlate with an increased risk of injury. Another success metric for this study is if we are positively able to identify features that correlate with an increased risk of injury.
Moving on now to the results section, we evaluated a number of different LSTM models with different hyperparameters for each one. And on screen, you can see a heat map of the top performing ones. We kept a close eye on validation loss, area under the curve, recall, and precision. And unfortunately, the highest F1 score that we were able to achieve was 0.333 repeating. After that, we took the top performing model and magnified the evaluation by plotting the precision recall curve at different thresholds ranging from 0.1 to 0.8. And you can see those on your screen now. And for this, we used holdout test data in order to get fresh eyes on it. Here we can see the final numbers. These are the average final results, and LSTM was the worst performing of all of our model types. And this could be due to a number of different factors, things like rarity of UCL rupture, despite the fact that the number of UCL tears has been rising over the past 10 years. It's still just a relatively rare occurrence. Furthermore, it could also be something like not enough time steps, and we might need to magnify the data. Just looking from season to season may not be enough to see different trends. We may need to look closer at things like game to game. After this, we decided to pivot to a tree classifier in case there were any problems with having the model be too complex and just overfit, but we had similar results. Lastly, looking at our baseline model of just logistic regression, we managed to get our best results, but it was still not the performance that we wanted. This did lead us to believe that any model would not really have any predictive value. Despite having no predictive value, the discriminative ability of our models was able to identify 3 risk drivers that contribute to the odds of a UCL rupture. Innings pitched was the dominant risk driver, leading to an almost 5-fold increase in the odds of a player suffering the injury. And this does align with previous literature on the subject. And furthermore, we also found that an increase in season-to-season workload, represented here as G delta, as well as a faster pitch tempo, contributed their own moderate increase of injury. From these results, we can quite confidently say that publicly available season-to-season data isn't sufficient to identify individuals who are at a higher risk for rupturing their UCL. With a consistent area under the curve of 0.6 to 0.7, it's clear that these models were not just randomly guessing, and they were picking up on some patterns. So, given this, the next logical step would be to start looking at the data on a more microscopic level. Would month-to-month data be sufficient, or would we have to zoom in even further to game-to-game data? There's just too many avenues left to explore before we can decide that we've reached a dead end. And our identification of 3 features that are the main risk drivers for this injury occurring will help to inform the direction of that future exploration into this area of study. And that was a major goal for us for this precise reason. And the fact that the most dominant risk driver, innings pitched, lines up with the past literature on the subject is particularly encouraging as it reinforces our current trajectory. And it appears that we've also been given new leads in the form of pitch tempo and changes in the number of games played across time.